The question we are asked today is how many of these molecules are polar? The molecules include SO3, OF2, BeCl2, CCl4, and O3. Now, what we're going to do first to determine if these are polar is we're going to draw Lewis structures. Now, I've taken the liberty of already drawing this Lewis structure out, but I'm going to walk through how I did it. So this is the Lewis structure for SO3. There's a total of 24 valence electrons due to oxygens each having 6, which makes 18, and then sulfur also having 6. So when making Lewis structures, the first rule is to make the octets on the outside. And I did so, but quickly realized that sulfur did not have octets in the middle. So what I did, knowing that sulfur can have more than 8 electrons, can have more than an octet because it is in the third row of the periodic table. So I knew it could have 12, so I moved a pair of electrons off of each oxygen on the outside and made it into a bond connecting it to the sulfur. So this is the total Lewis structure. Now what we're going to do is we're going to identify partial charges and the bond dipoles in this molecule. So the partial charges are based on the electronegativity. And looking at the periodic table, we know that sulfur has a lower electronegativity than oxygen due to oxygen being next to fluorine and it taking more energy to get to sulfur from fluorine, since fluorine is the most electronegative of all the elements. So we know that there is partial charges on each of the oxygen atoms, negative partial charges, and we know that there's a positive partial charge on the sulfur. Now, our next step is to draw the bond dipoles. And since we know that the oxygens are more electronegative than the sulfurs, or than the sulfur ion or molecule in the middle, then we know that the bond dipoles are going to go towards the oxygen. So we're going to draw 3 bond dipoles going out towards the oxygens from the sulfur. Okay, that is our bond dipoles for SO3. Now, what we're going to do is determine the net molecular dipole using the bond dipoles and the molecular geometry to determine if this is polar or nonpolar. So the molecular geometry of SO3 is trigonal planar due to the 3 bonds on the outside, 3 identical bonds actually that are separated by 120 degrees. And since we know that all 3 of these oxygens are equal in electronegativity, the arrows point in different directions, so they cancel out automatically. And when they cancel out, there's no net dipole moment. So that means that SO3 would be non-polar. Okay, 1 down. We got 1 down, we got 4 to go. Okay, let's move on to the next one. Okay, now we have OF2. And I've taken the liberty again of drawing the Lewis structure for you, but I'm going to walk through how I did that. So in total, there are 20 valence electrons because the F's each contribute 7, so that makes 14 on their part, and then the oxygen contributes 6, so that makes 20 when you add it all together. Now, I did the first thing, which was make octets on the outside atoms. And then when I did that, I had, as you can see, I had 4 valence electrons left over. So those go on the center atom. Now, the next step is to do our partial charges and draw the bond dipoles. And we know fluorine is the most electronegative of all the elements. So these are automatically going to have the partial negative charges, and oxygen will have the partial positive charge. And now this makes drawing our bond dipoles easy because we know that they're going to be pointing toward the fluorines. Oops. Now, this molecule OF2 has a bent molecular geometry, and here, let me draw it out for you just to show you how it looks. Oh, that's so here is a rough idea of what the molecular geometry will look for this, since it's a bent. Since it has the two, these are non-bonding, so they act as kind of like, you remember those? And as you can tell looking at the molecular geometry, the F's are going in the same direction, so they do not cancel out. So our net molecular dipole, it looks like this. So since this molecule has a net molecular dipole, we know that it must be polar. So OF2 is polar. Moving on, we have BeCl2. Now, here's the Lewis structure for BeCl2. It has 16 valence electrons due to there being 7 on the chlorines each, so that's 14 on the outside, and then Be has only 2. So when you add those together, it equals 16. Now I did the first step, making the octets on the outside, but then when you go to the center atom, you notice that it doesn't have an octet, but that's okay, because we know Be and B are allowed to not have octets. So next, we're going to identify the partial charges and draw the bond dipoles. So if we look at the periodic table, we see that chlorine, even though it's below fluorine, it is still closer to fluorine, and it takes less energy to get from fluorine to it. So therefore, it loses less in electronegativity. So chlorine has a higher electronegativity than beryllium. So it is going to have the partial negative charges, and beryllium is going to have the partial positive charges. Now, drawing the bond dipoles, we know that the bond dipoles are going to go outside towards the chlorine molecules. Okay. So, identifying the molecular geometry of this, looking at it, we can tell that it is a linear molecular geometry. And we know with linear molecular geometries, the dipole moments are going to cancel out. As you can tell by looking at them, they're going in opposite directions. So they're going to cancel out, and the net dipole moment is going to be 0. And when the net dipole moment is 0, we know that the molecule is nonpolar. So we know that BeCl2 is going to be nonpolar. Okay. Moving on, we have CCl4. And CCl4 has 32 valence electrons due to the chlorines on the outside each having 7, so that's 7 times 4, which is 28. And then you add carbons 4 to the 28, which makes 32. So this is a fairly simple Lewis structure. There's no gimmicks with it. The carbon has its octet. The chlorines all have their octets. It's very evenly distributed. Now, looking at the periodic table, we can identify the partial charges as the chlorines having the higher partial charges from the carbon. So they get the partial negative charges. the carbon atom in the middle gets the partial positive charge. So when we draw the bond dipoles, we know that they're going to be going to the outside toward the chlorine ions or molecules. Okay, so finding out the molecular geometry, we know that looking at it, it is a tetrahedral molecular geometry, and they're all symmetric, and they all have, since all of the domains are the same on the central atom, the bond dipoles cancel, and there's no net molecular dipole. So the molecule is nonpolar, therefore. And moving on to our last one of the day, ozone, or O3. O3 has 18 valence electrons due to each oxygen having 6, so it's 6 times 3, which is 18. Sorry about the jump. My phone ran out of storage. You know, we've all been there. But as I was saying, the oxygens each have 6, so that totals 18 valence electrons. Now, when you make the octets, you make the octets on all the outside, and then you realize that there's 2 extra ones that go on the middle atom, but when you do that, there's only 3, and the middle oxygen does not have a full octet. So you have to move one of the pairs from one of the oxygens, it doesn't matter which one, and you move it to make a bond so that the oxygen in the center has a complete octet. Okay. Now, we're not drawing the bond dipoles on this because they all equal each other, because they're all oxygen, so they all have the same electronegativity. But you can identify the partial charges because the partial charges are positive up here and negative up here because they have poles. And I just kind of gave it away because the poles, it's polar. But let me explain. Because the molecular geometry is bent, like if you remember the first, if we go back to the OF2, it was also bent molecular geometry. So this one is also a bent molecular geometry, and it has 2 poles, so it makes it polar. But when you draw the bent, it also is not symmetrical, so you know it's polar that way. So we know that O3 is polar. Okay, now wrapping this up, let's go back and answer these questions. So going through, how many of these molecules are polar? So let's go to S3 or SO3. Was SO3 polar? No, it was nonpolar. So we leave it as is. Okay, OF2, was it polar? Yes, it was. So we put a little check mark. Now BeCl2, was it polar? No, it was nonpolar. Sorry yet again about that. My phone ran out of storage again, so I'm going to try to hurry this up. Okay, we left off. BeCl2 is nonpolar. CCl4, we found out was nonpolar too. But O3 was polar. So the only 2 that were polar out of these molecules were O3 and OF2. I hope this helped your understanding of how to determine if molecules are polar or nonpolar.